So, hi everyone again, good evening. Thank you all for coming. We're Team Jam Session. My name's Aditi.
My name's Julia.
My name's Maya.
And just this last summer, we went to Eindhoven in the Netherlands to compete in the International OnStage League. So we're going to tell you about our project and our experience, and hopefully you guys enjoy.
Okay, so our presentation is split into 4 main sections. There's first one being an introduction of basically just who we are, what we competed in, what competition, what league. Number 2 is a deeper dive into our project and just the electrical, mechanical, software, and hardware aspects of it that all came together. Number 3 is our results, how we did at the competition, if we placed, what we learned, and how we are planning to apply that to our future plans, which includes if we are planning to compete together as a team next year, what we are pursuing individually, and what will happen to our project later. So starting with the introduction, my name's Julia. I am a sophomore at Bridgewater Raritan High School, and I am 15 years old. Over this project, I mainly worked on the integration between the Raspberry Pi and the servo motors, as well as just overall troubleshooting and debugging.
My name's Aditi. I'm a current junior at Woodbridge Academy Magnet School, and my main focus on this project was the sign language detection algorithm, as well as the communication between the Cytron and the Raspberry Pi for the lights.
My name's Maya. I am 15 years old, and I am currently I said it too. I'm a sophomore attending High Technology High School in Lincroft, New Jersey. So my role on the team was developing and building our hardware, modeling and 3D printing our custom parts, and designing the costumes for our robot. Okay. So RCJ's mission is to create a project-oriented educational initiative that sponsors local, regional, and international robotic events for young students through age 19. It also advocates for education over competition and promotes the use of artificial intelligence. RCJ also promotes a strong emphasis on autonomy for kids participating and to learn and do it yourself, basically.
So what is OnStage exactly? RoboCup Junior or RCJ is just this like overarching umbrella, and under that there are 5 different sub-leagues that you can choose to participate in. First 3 of them are pretty similar. They are RCJ Line, RCJ Maze, and RCJ Simulation. So these 3 are similar in the sense that there's like an obstacle course that your robot has to navigate through, and you get scored based on how well you do in that. Second, we have soccer, which robots participate in real soccer against each other, and you try to score in the other opponent's goal. And lastly is OnStage, which is what we participated in. The sub-league has the most room for creativity, and there's really not many restrictions on what you can choose to do with this. It really allows for freedom and creativity. You can be musical, you can do whatever you really want with it, as long as you have these 4 main features, which we will talk about next.
So this is the inspiration behind our project. So if we had to sum this up in one sentence, it would be that our robot uses machine learning and AI to recognize and classify American Sign Language symbols using a camera, and then plays those corresponding notes on a piano. So as it's taking in and classifying ASL symbols, it's pressing keys on a piano. So our inspiration here, as you can see, is really to bridge the gap between 2 different communities. So first is a community of people who use spoken English and are able to communicate in that on a daily basis. Then is people who use ASL and rely on that as their primary form of communication. So we chose music because it's a universal language, so that symbolizes the connection of these 2 communities. So we use music as our bridge between the community of people who speak and people who use ASL. All right, and in addition, this project is kind of phase 1 almost, and it symbolizes our team's commitment to combine and bridge the gap between these 2 communities, and as well as increase awareness and inclusivity for people who use ASL. So now we're going to start talking about our features. Our first feature is sign language identification. So the way this gets done is by using the Raspberry Pi Cam 3 as well as the Raspberry Pi 5. So the PyCam 3 first reads in images, and then the PyCam 5 is basically used to process them. One of the main things we use to process them is the media pipe library. So this library creates landmarks, which is essentially a map of the hand. So when you have different points on your hand, the media pipe library is able to process them and determine unique configurations of this hand. So each specific movement you do with your hand is recorded as a distinct configuration of landmarks, which means it's classified as a different symbol. And the way that we're able to tell the difference between these various arrangements of the hand is through random forest classifier, which is a machine learning algorithm.
Our next feature was called multi-threading. So multi-threading is a process in which two separate processes in a program are allowed to run simultaneously with each other. So we use this for our camera as well as our motors. So typically when using motors, you have to allot a certain amount of time for the motor to go from point A to point B and then back to point A. So in our case, we had 21 different motors spanning across 3 octaves on the piano, and they had to move from above the keys to press down the keys and then back up again. So this took in all about 0.7 seconds, and every time that our program would call the motor to move, there would be a 0.7 second delay in our code. So obviously we didn't want this because we have a camera constantly running a live video capture, and we don't want it to miss any crucial information. From when we move our hands to a different position, we don't want it to miss that information. So we decided to implement multi-threading, and so that the camera could run constantly while the motors were also moving without any delays in the camera. Another issue we had was that the pathway that our information took from our hands to the camera to the servo motors, it was kind of inefficient and long. So originally we had the camera connected to the Raspberry Pi, which then connected to another controller called the Arduino MegaPi, which then connected to the servo motors. This was over serial, which is a type of communication which transfers information through 1 bit at a time. This ended up being too inefficient and slow for us, for our purposes, and we decided that we had to change it and follow the KISS principle, which stands for keep it simple and strategic. So we ended up wiring the Raspberry Pi directly to the servo motor so that no information was lost and it was as efficient as possible.
So our third feature was servo motor movement. So our robot uses 21 Tower Pro servos across 3 octaves on the piano, and each servo occupies 1 key, white key. So the servo motors were connected to a servo driver to allow for individual control. So how that works, each is wired up to this board, and that is connected to the Raspberry Pi. So to implement this in our code, we had a dictionary that consisted of the key number 0 through 7 and a tuple. So this tuple included the letter note and the motor access key, so that number, and this allowed us to quickly and easily access all of the information about a servo in order to play it.
So our fourth feature is the use of lights. So this was meant to add a performative element to our project. Essentially, as each key is detected and pressed, each note has a corresponding color of lights. So the way that we were able to wire the lights was by hooking them up from the Raspberry Pi 5 through a middleman and then to the lights. The reason that we had to use this middleman was because the RP chip inside the lights was incompatible with the Pi 5. So instead of hooking that up directly, we decided to add a middleman so we could still use these lights. The way that the middleman works is that the Raspberry Pi and the Citron board, which is the name of our middleman, are able to communicate over UART, which is serial. So in this case, serial wasn't that inefficient because all we were sending over was 1 character at a time. So it was able to keep up a very decent speed, and as it technically was not the most crucial element and would not cause delays in other parts of our process, we felt that it was okay to still have that element of the Citron being used. So now we're going to move on to hardware.
So we've been talking a lot about this Raspberry Pi 5, but what is it? It's essentially a small computer, and we chose to use this because it works very well with the Raspberry Pi camera version 3. So that was our camera that we used, and together they have a very high efficiency in image processing. And the Raspberry Pi 5 also has 4 different processors, which is what allowed us to be able to multi-thread and have that kind of simultaneous simultaneous processes running. Additionally, the Raspberry Pi 5 has a port for Ethernet cables. Normally, we connect our laptop to the Raspberry Pi over Wi-Fi, but since we were going to be traveling to the Netherlands, we knew that we wouldn't be able to have steady Wi-Fi and dependable Wi-Fi over there in a foreign country, so we knew we had to use something else. So we used Ethernet, where we connected a cable to the Raspberry Pi and then directly to our computer to be able to access the program. In addition to that, the Raspberry Pi also has an abundance of UART and GPIO pins, allowing us to connect to a lot of different controllers and boards and the motors that we wanted to use. For example, the PCA 16-channel servo driver.
The second board that we use, as I mentioned, is the Cytron MakerPi RP2040. So this was chosen because of its compatibility with the NeoPixel lights and with the Pi 5. And what we used from here was the UART or serial connections, as well as the Grove ports. So because it had so many Grove ports, which are again GPIO pins, we were able to use it for a wide number of things relating to the lights, and it was very versatile. And we also had the advantage of having a little bit of prior experience with this board and with the coding language, which is C. So we decided that this was the best tool to use in this case.
So an important part of our hardware was our wooden frame, and the bulk of our controllers and hardware was mounted on this. So it was a custom wooden frame which slid onto our keyboard, which enabled us to have the correct alignment of the fingers relative to the piano every time we assembled and disassembled it. So our frame had 2 main levels, as you can see. The bottom held the modules which mounted the servo motors to the frame, and the top held the rest of our controllers, such as the Cytron, the Raspberry Pi, the servo driver, and the battery packs. And this was all designed and built by us. So in the end, we decided to paint it black and put some white flecks on it to match our space theme, basically. Oh, okay. So next, talking about our 3D printed modules. They had 3 servo motors each, and this allowed us to basically modularize our hardware. So it's a lot easier to deal with 7 different modules than 21 servo motors individually. And it was also to facilitate mounting to the frame. So the 3D printed fingers simulated the pressing down of keys on the piano, and they were customized to be attachable to the servo motors, and we covered them in felt on the bottom to prevent harsh clicking noises when a note was played. Moving on to software. Sorry.
Okay. So, as I mentioned before, one of the most important elements of our software was the media pipe library. So this is what actually allowed us to form that map of the hand that I mentioned, where you're looking at different points called landmarks. So each of one of those landmarks became one coordinate and one value in a large array that we created. And we would use the media pipe library to essentially convert these positional things into that array format. Therefore, because we were able to get all this information stored in the array, we were then able to put it into a pickle file, which is a type of data storage file that allowed us to use it very easily for the next phase of our thing, which was determining which is shown.
Okay, so speaking of the random forest classifier from earlier, so this was essential in helping us classify the data that was coming in through the camera. So we got this from the scikit-learn library, and basically what this does, it accesses our binary .pickle file, and it compares the training data with our new inputs to identify which character is being shown. So how this works, it takes a bunch of random trees which are basically one randomized way, and it helps classify a symbol. And it takes many of these and it averages it, and this helps prevent overfitting, which is when the classifier is checking too specifically for a certain case and it will just get the whole information wrong. So that averaging helps with that.
Next, we also used OpenCV, which gets the landmarks, the different points on the hand, directly from the camera. So it did that, and it also allowed us to be able to draw on top of the live video capture. So we could print like squares over the hand. You could print the landmarks. You could also print the exact letter that the computer was classifying. So this helped us for debugging because we were able to see in real time what the computer was actually seeing. And that we could tell if the computer was classifying the symbols incorrectly, what we needed to change, and it helped us discover why the certain issue was happening. This took some time for us to learn. It was one of the first things that we started struggling with because we had no prior experience with cameras or OpenCV, but in the end it was definitely very beneficial.
Okay. So now we're going to move on to our results, but we're going to start off with basically going over what we've learned through this project. There's a lot, so brace yourselves. So first is more of the technical skills. So for example, cameras, OpenCV, multi-threading, random forest classifier, all of these are new skills that we picked up over the course of this project. We had no idea what they were before, but we were able to use and apply them to a kind of real-world scenario by doing this project. We've also picked up new boards and controllers like the Raspberry Pi, as well as we learned the importance of spares. So when we went to Nationals, which was not that far away from here, but when we went to Nationals back in May, we had no spare parts, or little to no spare parts. So if a camera broke, or if a board stopped working, or if a servo motor broke, we would have no way to actively replace it. We realized that we needed to have backups and spares and be able to quickly make a fix because things do go wrong in competitions like these. So when we went to Eindhoven, the Netherlands, we had boxes and boxes of spare stuff. So that was a very important thing for us to learn, that things do go wrong and that you have to be always prepared for the worst case scenario. Next is more about our teamwork and some soft or personal skills. So we really had to learn how to communicate and work together as a team. So who was doing what, but also at the international level, we combined with 2 other teams at that competition to form an entirely new project on the fly. So I believe it was day 2 or 3 where we learned who we were working with, and then we had a couple of days to plan and get that project ready to present, basically. So that kind of teamwork and communication between not just us, but also between other people was a very important skill that we really honed during this process, as well as communication between the parents and the mentors and everything, because none of us drive. So if we had to go for a meeting, we would have to schedule it ahead of time. We need to make sure that all 3 of us were available. So little things that were also logistics, we got really good at this project, or a lot better at this project, because we were doing it so constantly and consistently. Time management goes hand in hand, as well as task allocation, and also making connections, which we'll actually talk about on the next slide. So during internationals and also after internationals, we've gotten interviewed several times. We were in the Asbury Park Press. An article about us was published in Microsoft and Adafruit and a bunch of other local newspapers. And we've become pretty familiar with the process of giving an interview and giving a presentation like this because we've done it so much across the course of our journey in this. So this kind of public speaking knowledge and knowing how to communicate information properly is something that I'm obviously still working on, but we have gotten a lot better at it throughout this project. And we actually even had to cross language barriers in the Netherlands between the other 2 teams that we worked with.
Okay. All right, let's talk about results. We have a fun little photo montage. So we placed 2nd internationally, in this competition. So this is us with our trophy. This is us with our super team. That's China and Germany and the US. And us on the podium.
So this is just like a bill of material statistics. So the bill of materials was something that every onstage team had to submit. It was basically just a total running list of the total amount of money you spent. So you had to include what parts you bought, how many you bought, the quantity in which you bought it in, and how much it totally came to amount to be. So here on the y-axis is the monetary amount of total money spent, and on the x-axis we have the rank, the final rank in which your team placed in. So previously mentioned, we came in second place, and our total running amount of money we spent was just under $1,000. So the point of showing these statistics that the OnStage committee chose to share with us was to answer those some of those 3 questions on the right side. They wanted to kind of debrief and discuss about how to make OnStage better for the next years. So first question, is it worth the effort for teams to be spending hours and hours doing work on a project that maybe another team just spent a lot of money on and could have done better just because they had more money in? Number 2, how should we use the data for judging? Should the amount you spend be factored into your score? Number 3, should we limit the expenses that you can spend? Should we be able to have a maximum spending amount, a minimum spending amount? How would it affect the scores in general? So we just thought this was really interesting. We thought it was cool that you could visually see really clearly how, like, which teams spent the most money and how they came in rank, how some teams spent a moderate amount, how some teams spent a smaller amount, and we just thought it was really cool that we were able to podium in place even though we spent less money than other teams. Okay, moving on to future plans.
All right, so this is an initiative that the 3 of us are trying to start. It's called Ladybug, which is kind of lady debug. So it's for promoting young girls, but also young kids in general, to pursue STEM in the future. We're kickstarting this with an invitation-only NASA app development challenge. So the 3 of us are going to be mentoring it. It is invitation only for now. But in the future, we are looking to make this program more inclusive, as well as teaching not just software, but also hardware. So this is something that the 3 of us are really excited for, and keep an eye out.
Okay, as for RCJ and our team jam session, for now we've decided to put a pause on our friend Arnold the Alien, and instead me and Julia will be doing RCJ line with Arusha. And Aditi will be pursuing an independent project to continue to gather experience and knowledge. And we're definitely not done with our robotics careers, and there's much more that we're curious about and we want to continue doing. Keep an eye out again. Thank you for listening.
This is a picture of us on stage. So we had the whole setup with like the cardboard cutout and the motors and everything, and you can kind of see that's our friend Arnold the Alien. All right.
Any questions?
Any questions?
Yeah, go ahead.
What exactly is the point of this, considering you're working with keyboard
With keyboard?
and not a piano and not a mechanical piano?
Oh, okay. So the keyboard we chose so it was easier to transport because, you know, even to kind of take a piano and drive it a little bit, that's pretty hard. So we did choose an electrical keyboard for this purpose. But I think in the future something could definitely be applied to a larger piano as well. You would have to change some of the measurements, but for our purpose, the electrical keyboard was best, so that's why we chose it.
Does that answer your question? Sort of? I don't know.
Yeah.
Okay.
Yeah.
So what is the main advantage of this? Like promoting the communication between like person who cannot talk and they both need to understand the keys, right? What is the advantage of this?
So for right now, this project is mostly to increase awareness. So we're taking sign language, American Sign Language to kind of this global stage. as of right now, it doesn't have an application, you would say, in a real world, but our detection algorithm could definitely be developed further into something.
Yeah, and adding on to that, I know some of us, Aditi especially, has a lot of interest in the medical field. So we wanted to kind of use this as a kind of first stage application that we could kind of see eventually happening in the real world. Originally, our intention was to have like this full sign language interpreter. But then, like a week in, we realized that was way too ambitious, and we definitely couldn't do that. So right now, it interprets the letters A, B, C, D, E, F, G, and we chose to do this because those are the letters on a keyboard.
Okay.
So that's why.
And how long did you spend? How many hours you spent every week, like an average?
It really fluctuated, right?
Like in the beginning, it was around like 3-4 hours a week we were putting into this, and then towards the end, it was every day,
Like
9 to
6
5.
hours.
Like, yeah, it was genuinely a full-time job. Yeah. Oh, sure. Okay. So we're gonna do a demo, and then we can ask an audience member to come up as well. Okay.
Okay, wait. Okay. Wait, Maya, hold up your hand. So these are the hand landmarks that we were talking about. It identifies all the points on the hand.
It's like
And-
really dark right now.
Yeah.
So usually it's not this bad.
And as you can see, her hand move.
Thanks.
Does that help?
Does it? Does it move?
Okay.
Okay, wait. Can we turn on the lights? Yeah, just like a little bit. Okay, that's
Okay.
a lot better.
There you go.
All right.
Maya, use your right hand.
Oh yeah.
All right.
Okay. Okay, so that was our
That was just like a
7-note scale. Yeah.
Yeah. And so actually, because you're doing it off of hand landmarks and not off of an image of a hand, it's pretty decent at using someone else's hand. So does anyone want to come up and try it? Arusha.
Okay.
All right. So C. Okay. B.
Yeah. Yeah. Then
B.
E.
I think
Yeah.
Yeah.
F.
G.
G.
Mm-hmm.
A. Done that like this.
Yeah.
So as you can see, it sometimes falters with someone else.
Oh,
There you go.
right.
But it is okay at picking up someone else's hands as well. Raise your hand a little bit.
Yeah. Just put it.
Yeah, there you go. And that's B.
Yay.
All right, thank you. Anyone else have any other questions about our Yeah, go ahead.
How does it play different octaves?
Good question.
Yeah.
Yeah, we have actually. Sorry.
Oh,
We only set up one of them right now, but remember how we said that we have 21 keys spanning across 3 different octaves? We have like a duplicate system 3 different times. So usually it's the 3 of us standing and signing up here at the same time. So we have a camera up here facing this person, a camera up here facing this person, and another camera over here. So there's like 3 pies, 3 servo drivers, 21 servo motors. Yeah, it's just a duplicate of each other.
Yes.
And yeah.
Like, how many years have you been, like, practicing, like, software? Not, like, just this project, just in general. How many years
Okay.
before this?
I think I've been going to storming since like maybe 4th grade, and I'm currently in 10th grade, so 6 years.
I've been going to storming since maybe 5th grade, and I started about like a year before that doing some stuff on my own.
I want to say like 3rd grade. I'm not really sure. I've been here like my whole life.
Yeah, so it's been a long journey for all of us. Okay.
Okay.
All right. All right, thank you guys so much.